Linear approximations. Objectives. By the end of this lesson, you should be able to explain why we use linear approximations, explain how we use tangent lines of a function to approximate function values, find and use a tangent line to a function to approximate function values, and to determine if our approximation is an over or under approximation. So first, why do we use linear approximations? Well, the simple answer is because lines are nice functions, right? They're easy to plug things into. You have an x and a y. They're easy to graph. In general, we love lines. They make everything simple. So what we're going to do is we want to use lines to approximate a non-linear differentiable functions. So remember, differential means you could take derivative anywhere. Non-linear means it's not a line. So when we have a kind of crazy function like we have here, and we want to approximate a value on it, like here, that might be really hard to approximate. But if we use the line of the tangent nearby it, it'd be much simpler. So that's kind of the idea. We want to approximate a value on this graph. That would be really hard to do by hand or something. So what we do is we find a derivative nearby that we could use, and then use its tangent line. And sometimes when you draw that line, you're going to be above it, like here. This would be an overestimation. So see how that red line, the point on the red line is above the point on the graph. And then sometimes you could do it such that, that's not a good example, like this. Let's say we wanted to approximate the point right here. I'm going to use this tangent line. Sometimes you're under approximation. So that red line is below the graph. So that's kind of the idea of what we're doing today. And it's actually, if we look what we're talking about, right, we're just talking about tangent lines. So the formula is just the same thing we do when we find an equation of a line. So if we want to use lines to approximate function values, we write an equation of a tangent line through the point, right, given a point and the slope. Well, it's just like what we always do. If you have a point and slope, we use a point slope form, right? Y minus y1 equals mx minus x1. That exact same formula, right? That's an equation of a line. This is a guy right here. Right? That's what this is. It's a fancy way of writing it, but that's what that is. What's the only difference? Well, since we're talking about tangent lines, right? Tan lines. That means the slope is the derivative. That's the only difference, is that the slope right here is the derivative. So it's the exact same equation we did before. Now, since we're actually finding values, you notice the difference here is that they move the f of a over, like they move the y1 over. So they essentially have this. X minus x1 plus y1. Right? They're moving that guy over just because they actually want to get a value here. That'll make more sense once we get to actual numbers, but that's all this is. It's a point slope form. Just keep in mind that the derivative is the slope, because that's what the derivative is, so with the tangent line, since we're talking about tangent lines. And then we're going to move over the y1 because we want to find an actual value. Anyway, the main idea here in this video is near x equals a, the tangent line of a function are close to each other. Right, so that's the whole idea is, given this graph here I'm going to draw, let's say we have square root of x. And I want to approximate square root of 3.9. Right, I don't know what the square root of 3.9 is. I doubt you do. So what we do instead is we're going to find a point close to 3.9, like let's say 4. So I know the square root of 4. I'll draw a little tangent line there. And since I cannot approximate 3.9, I'm going to use my tangent line to 4 and use that to approximate 3.9. Because you notice that if you're really close to it, you're about the same. Right? Any value right here will be about the same. Now if I try to approximate something like, let me approximate square root of 13, well, then it's not going to work anymore because that tangent line would be way off the actual graph. But close to it, they're about the same. You can see that up here, right? Close to my graphs, they're about the same. If I try to approximate something out here, it's going to be way off, way off. But as long as you're close to the thing you're trying to approximate, then it's going to be good. They're going to be close to each other. No, let's do an actual example. Write an equation of a tangent line to f of x equals x cubed at 2.8. Use the tangent line to approximate 1.9, 2.01. So first thing I'm going to do is write an equation of a tangent line. So I hear those words, I think point slope form. Right? I even have my x1, y1. Right? x1, y1. So 2 and 8. All I got to do is find the slope. So remember, that's the derivative at x1. So my derivative of my equation here will be 3x squared. and I plug x1. I'm plugging that too. You always do the squared first, so 3 times 4, so 12. So the equation of my linear line, my tangent line here is this. And like we talked about before, we're going to want to move this guy over because we want to just get a y value. So we can get this. You don't have to worry about like simplifying some more. This is like good enough. So that's the equation of my tangent line right there. Right, we've done this before, but that's the equation of the tangent line. Let's talk about what that looks like, right? So remember, we had this graph of fx equals x cubed. So x cubed looks like this. Right, and let's say, let's do my tangent line in a second. We're doing it at 2 and 8. So at 2 and 8. Something to that effect. We drew a tan line, so a tan line was kind of like this. Well, what I want to do here, we want to figure out what we want to approximate f of 1.9, so it's like really close to 2. And again, I could try to find that point, but it's gonna be too. I don't know what 1.9 cubed is. But instead, I could use the tan line and plug 1.9 into there, so I can figure out what f of 1.9 is approximately. I'll plug it into this equation. Oops. There we go. And that's just negative 0.1. Remember, 0.1 is essentially 1 over 10, so it's like dividing that by 10. So this is 1.2 negative plus 8, which is 6.8. Right, so approximately the 1.9 cubed is approximately 6.8. I can do the same thing for 2.01. Again, I do not know what 2.01 cubed is, but f of 2.01, plug it into the equation. That's just 0.1. Again, 0.1 is the same thing as 1/10, or divide by 10. So I get 1.2 plus 8, or 9.2. So 2.01 cubed is approximately 9.2. Put that in this side. There you go. Now look at the graph. My graph's not very good. If I blew that up, you can kind of see it. Let me draw a little more exaggerated version of it, like that. My approximations here, if you notice them, they're below the line. They're below the actual graph. So these will both be under approximations, right? If I kind of zoom in right here, right? This is my approximation point. This is the actual point, so it's below it. It's my approximation point. This is the actual point. So I'm below the value. So that's the first example. Let's do another one. Find an equation of a tan line to f of x equals sine of x at x equals pi. Use the tangent line to approximate f of 3. So again, equation of a tan line, y minus y1 equals mx minus x1. Keep in mind we are doing a tangent line, so the slope is the derivative at x1. Right, so in this case, they didn't actually give me my x1 and y1. I got to find them myself. So my x1, they gave it. They give me x1. They don't give me y1. Right, my x1's right here, pi. To find y1, what you gotta do is substitute it in. So f of x1, f of pi, which is my y1, it's gonna be sine of pi. Remember, I'm not sure how to do it. Sine e, 0. Here's pi. Negative 1 is 0. Sine is the y value, so 0. I gotta find my m, my slope. Remember that is the derivative because slope of a tan line, so we gotta find y prime, which in this case, derivative of sine is cosine. Plug in our pi, so cosine of pi. Remember, it's always a derivative at x1, it's never just a derivative, it's at x1. And as we go back to here, cosine is the x value, so it is negative 1. So my equation of my tan line is this now. Right, and then next, let's actually draw it before I do what's next, right? If I actually draw it to show what's going on. Sine starts in the middle. Looks kind of like that. It's my crude drawing. We're approximating at 3. So here's pi. Pi is 3.14. So we want to approximate 3. Well, my tan line I'm drawing is at pi, so it looks like this. Right, and all I gotta do if I'm approximating 3 is plug 3 in. So I'm going to get y equals -1, 3 times pi, 3 minus pi. And in this case, I should just leave it like that. That's my approximation. There we go. If you look at my graph, let's zoom in again. Right, notice how the point I want is actually below the line. So my approximation here is an over approximation. Right, the tangent line is above. The tangent line is above the actual point. So an over approximation again. Now if they actually do want you to simplify, it's not too bad. -1, 3, pi is 3.14, 1519, but I'll stop at 3.14. So I get -1 times -0.14. So just 0.14. So again, not too bad. Let's talk about next. Linearization. That's a fancy way of saying tangent line approximation. This is what we've been doing. What's going to change here is that they're not going to give us, they're not going to tell us oh, here's this function. You got to come up with your own function and your own values to help approximate this. It's like right here. Use linearization to approximate radical 4.1. So we're going to come up with our own equation here. Like, what equation are they using? Well, it looks like they're plugging 4.1 into a radical x. So there's our equation. F of x equals radical x. And they want us to approximate x equals 4.1. Now we're going to put in the equation, right? We still need our point. So what's a point? So when we do this, when we find a point that's near 4.1 that we actually know the square root of. Well, in this case, it's fairly easy, right? Our x1 should be 4. That'll make our y1, if we plug it into the equation, square root of 4, which is 2. So our initial point is 4, 2. So we're going to do the exact same thing we did before. We're going to write an equation of a tan line. Y minus y1 equals m x minus x1. We have our point now, right? We picked something close to 4.1 that we knew. So square root of 4.1 instead of that, square root of 4. So 4 and 2. We still got to find our derivative, right? M, that's f prime at x1. So you got to take a derivative of square root of x. Remember when we take a derivative of square root, we have to rewrite it as x to the 1/2. Derivative would be 1/2 x to the -1/2. Now remember, we have to plug a value in. You can never just leave it like that. The derivative of a tangent line is never just an equation. It should be a value. So you plug a point in. So we're going to plug in our 4. Get 1/2. 4 to the -1/2. Now don't freak out. I know it's algebra. Don't freak out. You do this first. Negative power just flips it, guys. That's all it does. So it's 4 to the 1/2 power. So that's 1/2. Remember, 1/2 power is the square root. Square root of 4 is 2. So you get 1/2 times 1 over 2. So 1 over 4. So what's 1 over 4? That's my equation. Y minus 2 equals 1/4 x minus 4. Remember, I do have to move this 2 over because you want it to be a value. So it's like this. So that's my equation. And then they want to approximate 4.1. So just plug in 4.1. If you want to actually simplify, you can. 14.1 plus 2, but for sake of space, I'm going to leave it just like this with the 4.1 turned in. That's kind of the idea. Let's do another one. Let's make sure we have this. Boom, we'll talk about under over. I forgot to talk about that in the last one. Let's just talk about under over right here. Same as before, right? If you look at my graph, I'm talking about square root of x. And all you want to see is a tangent line you're drawing above the line or below the line. If it's above, it's an over approximation. If it's below, it's under. So if I draw a tangent line like at 4 here, it'll be above it. So this is an over approximation. Let's talk the next one. Use linearization to approximate cosine of 1.5. So my function seems like it's just cosine of x. The point might be a little tricky. How do I get what's close to 1.5? It's a little tricky, but it's pi over 2. Right, pi over 2 is 3.14 divided by 2. It's about 1.5. So my x1 can be pi over 2. My y1, I got to plug it in. So cosine of pi over 2. I should know that. It's up here. 0, 1. Cosine dx value. So 0. So my initial point is pi over 2 and 0. Just like before, let's make an equation. Right? Y minus y1 equals m x minus x1. My points are pi over 2 and 0. My slope, we gotta take a derivative. Derivative cosine is negative sine. And don't forget we have to plug in our x1. So negative sine of pi over 2. Sine of pi over 2 is a y value, sine e, so 1, and there's a negative, so negative 1. So my equation is actually this. Right, that's my linear equation. But again, I do want to approximate 1.5, so let's plug in 1.5. So my equation is like this. I'm just going to leave it like this again. 1.5 minus pi over 2. There we go. Now, is it over or under approximation? Now, again, it's all about the tangent line. Is it above the line or below the line? If you draw a cosine, starts on top. So to that effect. Here we pi over 2. Here's 2 pi, sorry. Here's pi. Pi over 2 is like right here. Draw a tangent line there. Will be slightly over. So I've talked about the whole graph, but in general, how do we figure out if it's an over or under approximation? So remember whether the tangent line approximation is an over or under approximation, we need to determine if the tangent line is above or below the part of it. And then you're like, oh, well, how do I determine that? Well, it's actually fairly easy. If the curve is upward facing, so if I have a graph that's upward facing, we'll know this later as concave up. So to this effect, right, if I'm looking at this part of it, where it's upward facing, look how you draw tangent lines there. I would draw them like right here. Or right here. Or in this part. Notice that you're always below it. You're below the actual line. Because if you zoom in, you're like, okay, I'm trying to approximate this point right there with this line. Your value's going to be below the actual line. So if it's upward facing, you're going to be below. Again, I personally don't even memorize that. I just draw it. I'm like, okay, like I draw upward. Like, wait, so I'm below it. Okay, so below it. Then if it's downward facing, probably guess it's opposite way, right? So I have a graph that's downward facing. When I draw my tangent lines, it's going to be above the graph. So if it's downward facing, it's opening down, concave down, then it's going to be below. Sorry, it's going to be above. So upward. Okay, I just think of the picture. Then you're below, downward, then you'll be above it. And that's the lesson.